prime equal to a times x. Let's call this matrix a times x, for which value of k is a parameter here, is the origin. An asymptotically stable node, for which value of k is a spiral sink and a saddle point. So we can use eigenvalue methods. So we have this system x prime equal to a times x. For part A, we want to have the origin is an asymptotically stable node. So we could have two eigenvalues can be repeated. Actually, can be repeated eigenvalues, must be real, and in fact they must be negative real. So the negative part we make sure is asymptotically stable. So in this case it is actually a sink, a nodal sink. And now we try to find the eigenvalues, and we find the condition when the eigenvalues are negative real. And look at this matrix A, and we find eigenvalues of A minus lambda I equal to A minus lambda compute the determinant. We have lambda minus 2 times lambda plus 3 plus k. So lambda square plus lambda minus 6 plus k. So this is equal to 0. So lambda satisfies this characteristic equation. This is a quadratic equation. The quadratic formula delta 1 minus 4k minus 6. So minus 4k plus 25. We want real eigenvalues, so this one needs to be non-negative. This condition we will have real eigenvalues. This is greater than equal to 0 if and only if minus 4k plus 25 is greater than equal to 0, 4k is less than equal to 25, k less than equal to 25 divided by 4. So this is the first condition, we need real eigenvalues. But we also want the eigenvalue to be negative. So we compute the eigenvalues. The eigenvalues are lambda 1, lambda 2, minus b, minus 1, plus minus square root delta divided by 2a. So in this case we get minus 1 plus minus delta is minus 4k plus 25. Square root of delta divided by 2. We want this lambda 1, lambda 2 to be negative. So we just need to check the maximum one to be negative, then the smaller one will be also negative. So minus 1 plus root 25 minus 4k is negative. This one is a bigger one. divided by 2, but 2 you can multiply 2 here, so you get numerators less than 0. This one is bigger than the minus 1, so if this one less than 0, then the smaller one will also be less than 0. Root 25 minus 4k is bigger than less than 1. I'll square both sides. 25 minus 4k is less than 1. 4k bigger than 24. K bigger than 6. So here's the second part, the second condition. This one, negative eigenvalues. So combine with the first condition, we have k bigger than 6 less than 25 divided by 4. K bigger than 6 less than or equal to 25 divided by 4. Then we would have a nodal sink, asymptotically stable node. For the second question, spiral sink. So we have spiral sink. This means that the first condition, spiral here, we have complex eigenvalues. The imaginary part is non-zero. So to form alpha plus minus beta times I. So this is our eigenvalues. Imaginary part, beta non-zero. So that's the first thing. The second thing is this is sink. So we want the real part is negative. The real part of lambda negative, lambda 1, lambda 2. So let's look at the condition so that we have complex eigenvalues. For this, we have lambda is a solution of the characteristic equation. Equal to 0. We computed delta before. Delta equal to minus 4k plus 25. And we want complex eigenvalues, negative 4k bigger than 25, k bigger than 25 divided by 4. So this is complex eigenvalue. The second part, we need the real part to be negative. So the eigenvalues lambda 1, lambda 2 minus b plus this delta is negative, so plus minus I square root of minus this, so 4k minus 25 divided by 2. The real part minus 1 divided by 2 always negative, so we know that real part lambda 1, real part of lambda 2 minus 1 divided by 2 is negative automatically, so it doesn't depend on k. So the only condition we need is k bigger than 25 divided by 4. In this case, we have spiral sink. We need condition k bigger than 25 divided by 4. And the last one, we want to have saddle point. The part C, we want to have saddle point. 0, 0 is a saddle point. This is equivalent to the condition lambda eigenvalues lambda 1 and lambda 2 are first real, and second one is must be one negative, one positive. So the signs are opposite. Lambda 1 times lambda 2 is negative. So real eigenvalues and opposite side. Real eigenvalues, we did that. Delta bigger than 0. Delta strictly bigger than 0. So we have two distinct eigenvalues. So the first condition, lambda 1, lambda 2 are real, correspond to delta strictly bigger than 0. The second one, lambda 1 times lambda 2 is negative. So this is actually the determinant of A is negative. The products of two eigenvalues give us a determinant of the matrix. Delta bigger than 0 equivalent to 4k less than 25, k less than 25 divided by 4. Determinant of A less than 0. Determinant of A. This is A. Determinant of A minus 6 plus k less than 0, k less than 6. Okay. So actually this condition is always stronger than delta bigger than 0, because delta is actually, so in general you have A, B, C, D, for example. Matrix A, B, C, D. Then you have the characteristic polynomial A minus lambda I, A minus lambda, B, C, D minus lambda, determinant of this. So you have A minus lambda times D minus lambda minus BC. So this means lambda square minus A plus D lambda plus AD minus BC. So look at that, you see that this one equal to 0. The characteristic equation lambda square A plus D is the trait of A. AD minus BC is a determinant of A. So this is equivalent to lambda square minus trace of A times lambda plus determinant of A equal to 0. So you see that the sum lambda 1 plus lambda 2, the sum of two eigenvalues, is trace of A. The products of two eigenvalues, lambda 1, lambda 2, is a determinant of A. So if we have determinants is negative, so delta of this quadratic equation minus 3a square, so 3a square for determinant of A. So if determinant is negative, negative times minus 4 negative, so this is positive. Positive plus something non-negative, so this is always positive if determinants of A is negative. So you see that if we have the condition determinant of A is negative, then we have deltas bigger than 0 for sure. So that's why in this one is condition is stronger than this. So 24, 25 divided by 4, 6 is 24 divided by 4. So it's less than 25 divided by 4. So k less than this and k less than this. So we only need the condition k less than 6. So the condition when we have the critical point is a saddle point is equivalent to determinant A is negative. So 0, 0 is a saddle point if and only if determinant A is negative. So that's what we know. So next time whenever you try to compute the condition so that the critical point here 0, 0 is saddle point, we only need to check determinant A is negative.